Okay, hello calculus class. I am going to go over section 3.8, which is on linearization and differentials. And it's actually pretty easy stuff. It can seem complicated with the formulas they give you, but it's pretty easy. And the basic idea is this. If you have a curve, and I'm going to draw like the square root curve, right? So this is y is the square root of x. And we know certain points along that are real easy. Like when x is 25, the square root of x is 5, right? So that would be 5, because the square root of 25 is 5. So certain points along it we know real easily, but if we don't know the square root of 26, that's hard. But we know the square root of 25, that's 5. So the idea is, and this curve is complicated, square root of x, that's a complicated thing. So what we can do, and this is the whole point of the chapter, is at the point that we know, we can draw a tangent line. Well, that's why the linear part comes in. There's our tangent line, and the curve and the line aren't too different. So if we want to know the square root of 26, the real curve is complicated, but we can approximate it by the line, and as long as we're not too far away, the line and the curve are about the same. So that's the idea. We're going to approximate the curve of the straight line as long as we're not too far away from a point that we know. Then we're not too far off. But if we go really far away, like if we want to figure out the square root of 50, it's going to be way off. But square root of 26 is close, square root of 24 is close, square root of 23 isn't so bad. But the further away we get from the point, the worse. So all we're doing basically is finding the tangent line to curve at a point that we know. They have a formula in here which kind of sums that up, which is a little bit confusing, but it means the same thing. Which is, they say that the linearization, or our line, as a function of x, is the point, which is f of a, plus the slope, which is f prime at a, times x minus a. And here, basically, they're saying a is the x value, like x1 of the point, and f of a, that's a 1, that's a comma. F of a is the y value, which should be like the y1. So all this is really saying is that the y value is y1 plus the slope, because that's the derivative, is the slope at that point, the slope at the tangent point that we want, times x minus x1, which is just a line. So this is just equation for the line, a fancy way of writing it to show that we're linearizing a curve to make it a line. So it's just y equals y minus y1 equals mx minus x1. So that's what we're doing here. So we're approximating a curve with a point. So I'm going to do some of the even examples, should help you out with the odd ones. So let's see. Let's do number 6. So number 6 says, they want you to linearize f of x, which is equal to ln of x, at a equals 1. And a is just the x value. They like to use letter a, but that's basically, they're saying at x equals 1, let's approximate the ln curve with a line at x equals 1. Okay, so we have a point when x equals 1, what's y? So let's see, when x equals 1, ln of 1 is 0, because e to the 0 is equal to 1. So our point is 1 comma 0, and now we need a slope. So we take the slope at that point, and then we can find our line. So the slope is the derivative, so f prime of x is equal to, take the derivative out of x, that's just 1 over x. That was easy. And the slope at a equals 1 then, f prime at 1 is 1 over 1, which is 1. So our slope is 1, our point is 1, 0. So we go y is equal to y1 plus mx minus x1. So now we just plug it in. Y is equal to y1 is 0, plus the slope is 1, times x minus x1 is 1, or y is equal to what? X minus 1. So that's the answer. So it's pretty easy. It's just finding the slope by taking the derivative and then using the point that they give you to to work around. So basically, at ln of x, this line x to the minus 1, pretty closely approximate ln of x if you're close to x equals 1. If you get far away, it's not going to work so well. Okay, let's do another example. Let's look at number, I don't know, let's see. I assigned 15, 17, so let's look at number 16. Number 16 says, it's out of here. Number 16 says use a linear approximation to estimate the given number. Okay, so we want to estimate e to the negative 0.015. So that's a hard thing to do. However, you'll notice, so what we always have to do is pick a number close to that we know for sure. Okay, so first we're using our function is e to the x. Clearly it's e to the x, and we want to know when they would call it a, so we want to know when x, which we can call it a, just be like the book, is equal to negative 0.015. Okay, notice negative 0.015 is pretty darn close to 0, right? That's a really small number. So what you always do is you choose a number that you know that's easy. Well, I know x equals 0 is easy because at x equals 0, e to the x is equal to e to the 0, which is equal to 1. So we'll choose that as our point. You always choose a point that's easy to do in your head, close to the one that they want, which in this case is 0. Okay, so our point now is x equals 0, then y equals 1, because e to the 0 is equal to 1, and now we need a slope. So we take the derivative to get the slope, so f prime of x, okay, this is pretty easy, derivative of e to the x is e to the x, and we want the slope at x equals 0, so the slope, the derivative of x equals 0 is e to the 0, which is equal to 1. So again, nice, easy answer. So our slope is 1, our point is 0 and 1, and then we just do the y thing. So y is equal to y1 plus the slope times x minus x1, which again, there's different ways to write this, like the formulas they give in the book, which can seem a little confusing. They have, in the beginning of the chapter, they have y is equal to f of a, which is just the y value, plus the slope, f prime at a, the slope at that point a we're choosing, times x minus a, and again, a is the x value. So it's the same formula. This is the way we normally write it, so I'll just keep it simple. Okay, so the answer would be y is equal to y1, which is 1, plus the slope, which is 1, x minus x1, which is 0, or what's that? Just y equals 1 plus x, or x plus 1, however you want to write it. Okay, so that would be our linearization of that. Now, to get an estimate, we're approximating the line y equals 1 plus x. So what is it when x is negative 0.015? So y at negative 0.015 is 1 plus our x now is negative 0.015. And you can do that in your head or use a calculator. That's pretty easy. So 1 minus 0.015 would be 0.085. I believe that's right. So our estimate of e to the x at e to the negative 0.015 is 0.085. And if we get a calculator and try that out, you'll find that it's pretty close. So let me try that. This is exciting. So we want e to the negative 0.015. So we go in this calculator 0.015, oops, 0.015 negative e to the x, and they get 0.985, and that's because I did my math wrong, because that is the wrong answer. So they get 0.985 in the calculator, and if I did this math right, 1 1 minus 0.015. Okay, that's actually tricky. I can do it at the count. 1 minus 0.015. It's the same thing, which is 0.985. Okay, I need to be careful with my math. Okay, so it's the same thing as the calculator gives you. So the idea is we approximated e to the x at x equals 0. So, and then we can get an approximate answer, which is pretty darn good. That's really close to the right answer. Okay, so that's how you do these. The last thing I'll go over really quickly is the idea of differentials. Like this is for problem, let's see, one of the later problems, like problem number 24, it says find the differential of each function. And all you do for a differential, okay, they have the function for 24a, they have s over 1 plus 2s. That's our y. And so we can take the derivative, dy dx, there's our y. We can take the derivative dy ds here because we're using the letter s. So take the derivative of that and then put the ds on the other side, and our differential is the dy. So you just put the ds on the other side and the differential is a little bit, dy means a little bit of y. So all you're doing is taking the derivative and then putting the ds on the other side, and that's the differential. So for instance, in this case, this has to be a quotient rule. So the derivative dy ds would be derivative of the top, which is 1 times the bottom, 1 plus 2s, minus the top, s times the derivative of the bottom, which looks like it's just 2, all divided by the bottom squared, 1 plus 2s squared. And so the differential would be dy. So dy is equal to, let's see, on the top we have 1 plus 2s, minus 2s, that's pretty easy, divided by 1 plus 2s squared times ds. That's our differential, dy, and that would be the answer. Now, of course, I can simplify the top, those cancel out. So it's 1 over 1 plus 2s squared. So that's all you do for differentials. You're basically taking the derivative, solving for dy by putting the ds on the other side. So it's just taking derivatives, putting ds on the other side, and it's called a little bit of y, which can be a useful thing to know how to do. Okay, hopefully that helps. Again, let me know if you have any trouble doing these problems. I can do some more. So stay in touch, and hopefully then when you're done, take a picture of it and send it to me. So, okay, we'll be in touch. Bye.